So now we get on to probably one of the toughest things to understand in terms of circular motion, which is the dynamics for a car on a banked turn. So this is my favorite part of the circular motion thing, so I'm going to have a wheel with this. But I will take the proof about why the velocity is represented as what it is. I'll take it very slowly because it is quite a complex proof. But for a track banked at an angle alpha to the horizontal, the normal reaction force of the car can be optimized in such a way that friction from the tires doesn't have to play a role in keeping the car upright. It's a very counterintuitive thing, but basically the reaction force, if sufficient, can actually balance out the horizontal or the perpendicular component of the weight force. If it's traveling at such a speed, the reaction force can actually increase to a point where it gets to mg cos theta, or magnitude mg cos theta, and the friction of the tires acting inwards actually has to do nothing, pretty much. But then, of course, if it slows down, the friction from the tires can allow it to maintain that banked circular path. So applications of this range from bobsleigh teams to even quick sports cars, such as these Mercedes cars here. It can also help with maintaining tires. So, for instance, when Bugatti were testing their Bugatti Veyron Supersport, their supercar in 2015, I think, they had the car go on a banked track similar to this before it went flat out on a straight. This is actually to make sure that the tires wouldn't wear out from the speed it was going at. But in actuality, before the tires would run out, you'd run out of fuel first if traveling at top speed. But anyway, it can be shown that the speed required to keep the car moving in the circle, in the special case, is root g or tan theta, or tan alpha. Now, this point here might not make a lot of sense, but essentially if we write this equation in terms of tan alpha, so v squared is g or tan alpha, or tan alpha, so tan alpha is v squared over g or, but mu is also v squared over g or. So we can say that tan alpha, if you remember, is less than or equal to mu. On the other end, some whatever. But for it to be stable, well, tan alpha can equal mu. So it's a nice handy relationship between a horizontal circular motion and a vertical circular motion. So like I said before, the proof for why this is true is fairly complex, and I will go through it nice and slowly because it is a complex looking proof. So here's the first part of the proof. We have our diagram here in the top corner. So we have the reaction force perpendicular to the surface, which I've split into components. So these are similar triangles, and these are also similar triangles. If you can kind of imagine this here is a mirror line and this is flipped around like this, you get the same triangle. So the angles in there would remain the same. Next, the frictional force is acting directly along the plane, and we can split this into components. So we have Fk sine theta and Fk cos theta. I'll actually draw on the arrows of it which way these are acting. So this one's acting up and in, and then conversely this one's acting down and out. So we actually start with the centripetal force is mv squared over r. So the centripetal force is all the inward forces, so that's Fk cos theta plus r sine theta equals mv squared over r. Now, forces up equals forces down. R cos theta upwards equals mg plus f sine theta. So both of those are acting directly downwards, opposite to r cos theta. So if we take equation 1, we get r cos theta minus f sine theta equals mg. So this is actually equation 2, rather. I should realize that's equation 2. So if we take away f sine theta from both sides, we get r cos theta minus f sine theta equals mg. Now, of course, f is equal to mu r, so we get r cos theta minus mu r sine theta equals mg. So if we factor out an or, the reaction force, we get r times cos theta minus mu sine theta equals mg. So if we just divide everything by this entire bracket, that's a very bad underline. So dividing everything by this bracket, we get that the reaction force is equal to mg divided by cos theta minus mu sine theta. Now this obviously makes sense because r is a force in newtons, mg is a force in newtons, and all of these are dimensionless. So we're looking okay so far. And we're going to call this equation 3. Now, from equation... this was equation 2. Equation 2. This one's equation 1. So mv squared over r, if we take away f cos theta from both sides, we get mv squared over r minus f cos theta equals r sine theta. Again, we know that f equals mu r. So mv squared over r equals mu r cos, or minus mu r cos theta equals r sine theta. So adding mu r cos theta to both, we get mv squared over r equals mu r cos theta plus r sine theta. So mv squared over r equals r times sine theta plus mu cos theta. So we're slowly making our way to the proof. So here's the second part of it. We put the one from equation 3, so mg over cos theta minus mu sine theta, into equation 4 to get mv squared over r equals mg times sine theta plus mu cos theta divided by cos theta minus mu sine theta. So cancelling the m's and dividing top and bottom of this fraction by cos theta, it's a very common thing you have to do to get tan, we get v squared over r equals g times tan theta plus mu over 1 minus mu tan theta. So multiplying by r and taking the square root, we get the general solution, which is that the velocity of an object on a banked track at an inclination of theta at a radius r away from the center is root g or times tan theta plus mu divided by 1 minus mu tan theta. Now dimensionally this also works because this is meters per second squared times meters, and the square root of meters squared per second squared is just meters per second. Now of course the special case occurs at mu equals 0, so if you go back and if you put mu equals 0, this becomes 0, this becomes 1 minus 0, so that's just 1, and we get v equals the square root of g or tan theta, which is the, as I've already written, the special case when the friction tends to 0 and the reaction force does all the work.